Time, the silent river that carries everything that ever was, and everything that will ever be. From the heartbeat of a mayfly to the slow death of a star, all existence drifts upon its invisible current. Yet for all its certainty, time is not what it seems. What feels steady, seconds, minutes, years, is merely an illusion, a fragile rhythm beating inside the human mind. Out in the cosmos, time bends, warps, and stretches like molten glass. It flows differently for every traveler, every atom, every point in space. Einstein revealed this uncomfortable truth. Time is not a constant. It is a dimension, pliable and obedient to gravity. Near something massive, a planet, a star, a black hole, time itself begins to slow. To an observer far away, a clock near that gravity well ticks sluggishly, as if the universe itself is holding its breath. Imagine a spacecraft drifting near the edge of a black hole, the event horizon, where gravity becomes infinite and light itself cannot escape. Inside the ship, moments pass as usual. The crew feels the seconds tick, the hum of instruments steady and familiar. But beyond them, the universe races ahead. Galaxies spin, stars are born and die, civilizations rise and fall, all in the time it takes them to blink. To them, a few hours; to the cosmos, an eternity. Time, in this place, is not a universal constant. It is a landscape of distortions, a field of warping possibilities, and yet, the strangest question of all lingers like an echo in the dark. If time can slow, if it can stretch, could it ever reverse? Could there exist a place, somewhere in the endless fabric of space-time, where the arrow of time, the one that forever points from past to future, bends backward, where cause and effect dissolve, and what was once the future becomes the past? It is a thought that defies instinct, that challenges every rule of nature we believe immutable. But perhaps the universe has already hidden such places beyond event horizons, inside quantum chaos, or deep within the fabric of the multiverse itself. We're only a fragment in the dark, but together we can light the way. Subscribe to the journey for humanity. The attempt to measure time has always been an act of defiance, a way to hold still what is forever escaping. Every calendar, every clock, every equation carved into the mind of physics is a rebellion against entropy, the law that ensures all order will one day collapse into silence. Yet, before we can search for the places where time might reverse, we must first understand how it flows, and what, or who, commands its current. Time once seemed unshakable, a steady drumbeat to which the universe moved in perfect rhythm. It governed the dance of planets, the motion of tides, the unfolding of life itself. For centuries, scientists believed it to be absolute, the same everywhere, for everyone. It was the one thing Newton himself trusted completely, an invisible metronome ticking behind the machinery of creation. But in the early years of the 20th century, a young patent clerk named Albert Einstein shattered that illusion. Through quiet thought experiments, a beam of light, a moving train, the stillness of a clock, he began to see something extraordinary. Time was not the steady flow humanity imagined. It was a dimension, inseparable from space, woven into the very fabric of reality. From 1905 to 1915, Einstein's theory of relativity transformed physics into something unrecognizable. Time, he said, does not tick the same for all observers. It bends, stretches, and slows, depending on motion and gravity. The faster one moves, the slower one's clock runs, compared to someone at rest. Near a massive object, like a star or a planet, gravity warps the fabric of space-time, dragging time itself into its curve. The universe was no longer a clockwork mechanism. It was an ocean of distortions. time ebbing and flowing in ways no human sense could perceive. This revelation was not easily accepted. Early physicists resisted it, clinging to Newton's eternal flow. The thought that two clocks could disagree about the passage of time was nearly heretical. Yet, experiment by experiment, the universe confirmed Einstein's vision. Atomic clocks placed at different altitudes on Earth began to tick out of sync. The one closer to the planet, deeper in its gravitational well, ran ever so slightly slower. The difference was small, measurable only in billionths of a second, but it was real. Time itself was not universal. It was personal, shaped by where one stood in the cosmos. The proof extended far beyond laboratories. High above the planet, satellites orbit Earth in a weaker gravitational field. Their clocks run faster than those on the ground. Without correction, the global positioning system, the network that guides airplanes, ships, and even everyday smartphones, would drift miles off course each day. The engineers who keep it running must constantly account for relativity, adjusting each clock so that all of human civilization can navigate a universe that refuses to tick uniformly. Every GPS signal is a silent tribute to Einstein, a constant reminder that even our most practical tools depend on the strange elasticity of time. Imagine, then, a cosmic clock not made of gears and hands, but of space-time itself. Near a black hole, its face warps downward, distorted by gravity's pull. The closer one approaches, the slower its seconds fall. At the event horizon, where gravity becomes infinite, the hands seem to freeze entirely. To an outside observer, time there stops. To the falling traveler, it continues as before, unaware that to the rest of the universe, they have become a still image, suspended forever on the edge of reality. Such visions changed everything. The Newtonian comfort of absolute time was gone, replaced by a universe far more complex and far more alive. Time was revealed not as a river flowing uniformly forward, but as a landscape of valleys and peaks, shaped by motion, mass, and gravity. And yet, within this revelation, a deeper question began to form, one that even Einstein himself never fully answered. If time can slow... could it stop? And if it can stop, what prevents it from running the other way? In the years that followed Einstein's breakthrough, physicists began to put his theory to increasingly precise tests. What started as abstract mathematics soon became measurable reality. The Hartle-Keating experiment in 1971 provided one of the clearest demonstrations. Scientists placed atomic clocks aboard commercial airliners, flying them eastward and westward around the world. When compared to identical clocks that remained stationary on Earth, the results matched Einstein's predictions exactly. The airborne clocks had experienced a different passage of time. Motion and gravity had altered the rate at which their seconds unfolded. It was not a trick of perception. It was the fundamental behavior of the universe itself. In the quiet precision of mathematics, time has no direction. The equations that describe the universe, from Newton's classical motion to Schrödinger's quantum waves, do not care whether moments move forward or backward. To them, time is a coordinate, not a current. Reverse it, and the laws remain unchanged. A falling apple can rise again. A shattered glass can reassemble, its fragments pulling together as though regret itself guided them. Physics allows it. The symmetry holds. The universe, at its core, appears to be indifferent to the arrow we call forward. This strange neutrality was first glimpsed not through philosophy, but through the structure of the equations themselves. In the early 20th century, as scientists explored relativity and quantum mechanics, they found a hidden elegance. If one replaced time with its negative, if it became the result still worked. The universe didn't break. Its logic didn't fail. To mathematics, Time's reversal was not forbidden. It was simply another path through the same landscape. In particle physics, this symmetry takes on a deeper form, one known as CPT symmetry, charge, parity, and time. If all three properties of the universe were flipped, positive charges made negative, spatial orientation mirrored, and time itself reversed, the fundamental laws would remain identical. The behavior of every atom, every photon, every quantum field would still make perfect sense. This principle is so fundamental that it has become a cornerstone of modern physics. Nature, it seems, keeps time reversal embedded within its code, hidden beneath the macroscopic order of things. But in our everyday experience, the world is not reversible. Ice melts, stars burn their fuel, smoke never returns to the flame. The difference lies not in the laws themselves, but in one rebellious rule, the second law of thermodynamics. It introduces entropy, the measure of disorder. It states that in a closed system, entropy can only increase. Energy disperses, structure decays, order unravels. This is what gives the universe its direction. It is not time itself that insists on moving forward. It is entropy, the steady march toward equilibrium. Every memory humanity holds exists because of that law. The past is recorded in traces of low entropy, patterns left behind before energy diffused. The future, by contrast, remains blank, unformed, high in potential but empty of information. It is why the human mind can recall yesterday but not tomorrow. The arrow of time does not arise from the fabric of space-time itself. It emerges from the way energy organizes, scatters, and forgets. Yet, at the smallest scales, entropy begins to lose its grip. In the quantum world, particles behave with a strange kind of freedom. They can collide and separate in ways that are fully reversible. A quantum interaction looks the same whether time runs forward or backward. To the subatomic universe, the concept of before and after dissolves. Events are governed by probabilities, not sequences. Only when countless particles combine into complex systems, stars, planets, living beings, does the arrow of time emerge, shaped by entropy's preference for disorder. This realization unsettles the foundations of perception. If the arrow of time is not a universal constant, but a byproduct of entropy, then it is not sacred. It can, in theory, bend. Somewhere in the cosmos, under the right conditions, perhaps within a closed pocket of low entropy, time might not just slow but reverse. A region where cause follows effect backward, where light unravels into darkness, where decay becomes creation. It is not forbidden by physics. It is only prevented by the overwhelming statistical tide of the universe's increasing disorder. But what if, in the vastness of the cosmos, the tide shifts even for a moment? What if, deep within a black hole, inside the singular chaos of a quantum field, or beyond the boundary of our own universe, the conditions align for entropy to fall instead of rise? If such a place exists, it would not just change the way science views time, it would redefine the meaning of past and future themselves. Because if time's direction is only the consequence of entropy, then somewhere in the universe, under the right conditions, the arrow may not just fade, it may turn the other way. Physicists began to explore the implications of this possibility with increasing rigor. If the laws of physics are symmetric in time, then, in principle, a reversed universe could exist, one in which every process unfolds backward according to the same rules that govern ours. In such a universe, radiation would converge instead of spreading, and systems would evolve from high entropy to low, becoming more ordered with each passing moment. Nothing in the mathematics prohibits this. The real question is why the universe we observe behaves in only one direction, one explanation, points to the conditions of the early universe. Immediately after the Big Bang, the cosmos began in a state of exceptionally low entropy, smooth, dense, and uniform. Over billions of years, gravity and energy have driven it toward higher entropy, forming galaxies, stars, and black holes along the way. The second law of thermodynamics reflects this historical imbalance. It doesn't define time's direction. It merely records the consequence of the universe's starting point. If the Big Bang had begun in a high-entropy state, time might have flowed differently, or perhaps not at all. In laboratory experiments, scientists have demonstrated time reversibility on small scales. In 2018, researchers using IBM's quantum computers simulated the behavior of a few interacting particles and managed to reverse their state, returning them to an earlier configuration with near-perfect accuracy. The experiment did not reverse time itself, but it showed that the physical processes governing the system were reversible at the quantum level. When more particles were added, however, the reversibility quickly broke down. Complexity reintroduced entropy, restoring the forward arrow of time. Another field that examines time reversal is particle physics, particularly through studies of CP violation, tiny asymmetries observed in the behavior of certain subatomic particles, such as kaons and beam. In these cases, time reversal symmetry appears to be slightly broken. These effects are extremely small but crucial. They may explain why the universe contains more matter than antimatter, a necessary condition for galaxies, planets, and life to exist. If time reversal were perfect, matter and antimatter would have annihilated each other completely after the Big Bang. The imbalance suggests that while time, symmetry is a fundamental feature of the laws of physics, the universe itself may contain exceptions that favor one direction over the other. Researchers studying cosmology and quantum gravity are now asking whether these asymmetries might emerge naturally from deeper physical principles. Some theories propose that our universe could be one of two mirror universes that formed from the same Big Bang, one moving forward in time, the other backward. In this model, both universes expand away from the same point of origin, each experiencing its own arrow of time pointing in opposite directions. From the perspective of the inhabitants of either universe, time would always appear to move forward, but relative to each other, they would be reversed. The idea remains speculative, but it demonstrates a critical point. Physics does not outlaw reversed time. The limitation is practical, not theoretical. Reversing time on a large scale would require reversing entropy, an action that would demand precise control over every particle in a system, an impossible level of coordination in a universe of countless degrees of freedom. Entropy increases because the number of disordered states vastly outnumbers the ordered ones. Statistically, the odds of reversing it are near zero. Even so, scientists continue to test the boundaries of these principles. Experiments in quantum information theory and thermodynamics are revealing that entropy may not always increase in isolated systems. In controlled quantum processes, researchers have observed temporary local decreases in entropy, short-lived microscopic reversals of time's arrow. These are not violations of thermodynamics, but fluctuations permitted by quantum uncertainty. They show that time's direction is not absolute, but statistical, emerging from the collective behavior of particles, not from any universal law. This understanding shifts the question from why does time move forward to why does it almost always move forward. It implies that the flow of time is not a built-in feature of the universe, but an emergent one, a property that appears only when many particles interact under certain conditions. If those conditions were ever reversed, so too could the arrow of time. Whether such a state could exist naturally somewhere in the universe remains an open question, one that bridges physics, cosmology, and philosophy. It suggests that the flow of time may not be a fixed rule, but a temporary pattern in a universe still writing its own direction. It began with thought, the kind that unfolds in silence, in the stillness of an unseen mind. Long before machines could pierce the edge of space, one man, sitting at his desk in Bern, began to imagine impossible clocks. Albert Einstein's thought experiments were his observatories. No telescopes, no instruments, just logic stretched to its breaking point. He pictured beams of light bouncing between mirrors on a moving train, and wondered what time would look like for the passenger inside versus the observer watching from the ground. He imagined rockets racing at the speed of light, clocks ticking differently for those in motion and those at rest. From those visions, relativity emerged, not as fantasy, but as a new geometry of existence. Time, Einstein realized, was not fixed. It was shaped by motion, bound to gravity, and inseparable from space. But even Einstein did not foresee where his equations would lead. In 1916, Karl Schwarzschild, serving on the Eastern Front of World War I, found the first exact solution to Einstein's field equations. He discovered something extraordinary, a point where gravity became infinite and space-time itself folded inward. It was the birth of the idea now called the black hole. In Schwarzschild's mathematics lay the implication that time could not escape this collapse. Near such an object, seconds stretched toward infinity. At its center, the singularity time ceased to exist in any meaningful sense. To the outside universe, anything crossing that threshold would appear frozen forever on the edge of time. Einstein himself was skeptical. He believed nature would never allow such extremes. To him, the singularity was a mathematical trick, not a physical reality. Many agreed. For decades, black holes were treated as curiosities, abstract solutions without substance. The idea that time could stop or even fold was dismissed as absurd. Yet, mathematics continued to argue otherwise. In the 1960s, Roy Kerr extended Schwarzschild's work to describe a rotating black hole, one that did not collapse into a single point, but twisted spacetime into a whirlpool. His equations revealed something even stranger: closed time-like curves, loops through spacetime that, in theory, could allow a traveler to return to their own past. The possibility of time reversal was no longer confined to imagination. It was written into the mathematics of the universe. The scientific world met these ideas with hesitation. To suggest that time could loop back upon itself was to challenge not just physics, but intuition. Yet the universe began to provide its own evidence. Quasars, distant beacons of unimaginable energy, hinted at objects so dense that nothing could escape them. Later, X-ray observations from binary star systems revealed invisible companions pulling matter inward with irresistible force. The impossible had become observable. Black holes were real as telescopes grew more powerful. Mathematics found its reflection in reality. Space became a laboratory for time itself. Each discovery deepened the mystery rather than solved it. Every equation confirmed that near black holes, time behaves unlike anywhere else in the cosmos. It slows, it distorts, it stretches until the concept of now fractures. The boundaries that define cause and effect begin to blur. For those standing far away, the fall toward the event horizon appears endless, frozen in perpetual descent. But for the one who falls, the journey continues unbroken, drawn inward to where physics itself begins to unravel. The scientists who first wrote these equations could not have imagined the emotional gravity their discoveries would carry. What began as mathematics on paper had become a revelation about existence itself. humanity has touched something fundamental, the realization that time is not a constant stream, but a fragile construct capable of breaking, twisting, and perhaps even reversing. And as telescopes reached deeper into the darkness, one truth became increasingly clear. The closer we looked into these cosmic abysses, the more it seemed that the flow of time was not a property of the universe, but a condition of our perspective. To truly understand where time might reverse, one must first venture into the places where it already begins to fracture, where light itself bends, and the future and the past become indistinguishable, following the theoretical foundations laid by Einstein, Schwarzschild, and Kerr. Observational astronomy began to provide the first tangible evidence that the universe hosts regions where time behaves unusually. In the mid-20th century, quasars were discovered, distant, extraordinarily luminous objects that emitted more energy than entire galaxies. Their existence implied compact sources of immense gravitational pull. For astronomers, these were the first hints that black holes were not merely mathematical curiosities, but real physical entities. Time around these objects could not behave normally. Their gravitational fields were strong enough to significantly warp space. By the 1970s, X-ray astronomy provided more direct evidence. Satellites like Uhuru detected high-energy emissions from binary star systems where a visible star orbited an invisible companion. Matter drawn from the visible star formed an accretion disk around the unseen object, heating to millions of degrees as it spiraled inward. The only explanation consistent with both the observed energy and the dynamics of the system was a compact object with gravitational strength sufficient to prevent light from escaping a black hole. These observations confirmed that regions of extreme space-time curvature exist in nature, and by extension, regions where time itself slows dramatically. Simultaneously, theoretical physics continued to explore the implications of rotating black holes, or Kerr black holes. Unlike the non-rotating Schwarzschild solution, Kerr black holes possess angular momentum, causing space-time to twist around them, an effect known as frame dragging. This rotation allows for the formation of closed time-like curves in the mathematical model. While such curves are extremely sensitive to conditions and may be destroyed by minor disturbances, their existence demonstrates that, under certain solutions to Einstein's equations, time could loop back upon itself. No law of physics explicitly forbids this. It is a feature embedded in the geometry of spacetime near rapidly spinning. SINGULARITIES. Roger Penrose's work on cosmic censorship and singularity theorems further clarified the structure of these extreme regions. Penrose proposed that singularities are generically hidden behind event horizons, meaning that the strange behaviors of time near them cannot directly interact with the rest of the universe. Stephen Hawking extended these concepts to cosmology, showing that singularities could form not only in black holes, but also at the beginning of the universe. Together, their work demonstrated that singularities, points where known physics breaks down, are integral to the evolution of the cosmos. Time near these points behaves according to rules, dramatically different from those experienced in ordinary conditions. The resistance these ideas initially faced was substantial. Many physicists found the concept of time looping or reversing counterintuitive, incompatible with lived experience. Black holes were dismissed as theoretical extremes with no practical relevance. Yet observational breakthroughs gradually changed this perception. Radio, optical, and X-ray data converged to show that compact, high-gravity objects not only exist but influence surrounding matter in ways predicted by the mathematical models. Relativity had moved from abstraction to empirical science. Further exploration revealed additional consequences. Time dilation effects near compact objects are measurable and must be accounted for in astrophysical modeling. Matter falling toward a black hole appears to an external observer to slow and freeze near the event horizon, demonstrating that even macroscopic objects experience the effects of warped time. These observations aligned precisely with Einstein's predictions, reinforcing the conclusion that time is not an absolute backdrop but a dynamic quantity affected by mass and motion. At the same time, rotating black holes introduced theoretical possibilities that extended beyond slowing or freezing time. In principle, closed time-like curves suggest regions where causality could behave differently, potentially allowing sequences of events to reverse. While such configurations are unstable and would likely be destroyed by any small perturbation, they illustrate a fundamental point. The laws of physics do not forbid time from bending back on itself. They define a framework in which reversed temporal sequences are mathematically consistent, even if practically unattainable on a human scale. These discoveries collectively marked the origin of humanity's serious engagement with time reversal as a physical concept. Beginning with thought experiments and evolving through mathematical solutions, observations, and simulations, the field has moved from speculation to measurable science. It demonstrates that time, once assumed universal and linear, is highly sensitive to environmental conditions. Gravity, motion, and rotation can distort it, sometimes to extremes that challenge the conventional understanding of past, present, and future. At the same time, scientists must reconcile their awe with ethical and philosophical implications. If time can reverse, the deterministic consequences challenge assumptions about responsibility, causality, and meaning. The psychological weight of this knowledge is not hypothetical. It has tangible effects on those who study it. Many describe a sense of vertigo when considering the universe from the perspective of a singularity, a quantum fluctuation, or a closed time-like curve. To comprehend mathematics is one thing. To internalize the reality that past and future may not be as distinct as lived experience suggests is another. One striking example occurred during the analysis of data from a rapidly rotating black hole. An astrophysicist examining the X-ray emissions noticed anomalies consistent with extreme frame dragging, theoretical distortions that could, in principle, allow temporal loops. The realization was immediate and visceral. The equations aligned with the possibility of time moving backward under specific conditions, or mixed with fear. The elegance of the universe's laws was undeniable, but the consequences for human understanding were profound. It is one thing to read mathematics in a journal. It is another to stare at evidence that reality itself might permit a reversal of events. Yet emotion, powerful as it is, cannot dictate the universe. Physics remains indifferent. Entropy continues to rise across the observable cosmos, and the arrow of time points forward in everyday experience. But the human mind struggles to accept that the universe does not conform to perception. The tension persists, awe for discovery, fear for what it implies, and the enduring confrontation between the comfort of lived experience and the unsettling truths revealed by careful observation. Emotion may anchor us to one direction of time, but physics refuses to obey emotion. And in that refusal lies both the challenge and the wonder of exploring the possibility that time, which frames existence itself, is far more flexible than intuition or tradition has ever allowed. For scientists working at the frontier of temporal research, the challenge extends beyond theory into observation and experimentation, high-energy astrophysics, gravitational wave detection, and black hole imaging all demand confrontation with phenomena that defy ordinary intuition. Instruments like the Event Horizon Telescope, which captured the first image of a black hole shadow, provide direct evidence of regions where space-time is distorted to an extreme degree. The light bending around these objects demonstrates that time near the event horizon operates on scales vastly different from those experienced elsewhere in the universe. The implications are clear. The linear progression of seconds, minutes, and hours is not universal. Similarly, research into frame dragging and the Kerr metric requires scientists to account for effects that are difficult to conceptualize. Rotating black holes twist spacetime around them, creating paths closed time-like curves that are mathematically valid solutions of Einstein's field equations. These curves are not hypothetical constructs for entertainment or thought experiments. They are integral to the mathematical structure describing a subset of black holes. While no one has observed a macroscopic reversal of time, the possibility that such loops exist demonstrates that the laws of physics themselves do not forbid time from running backward under specific conditions. The human response to these findings is complex. Physicists report a duality of experience, professional excitement tempered by personal unease. The notion that time might not be absolute challenges deeply ingrained perceptions of causality, consequence, and free will. If an event can, in theory, precede its cause, or if sequences of events can occur in reverse under extreme conditions, fundamental assumptions about predictability and control are disrupted. Researchers must constantly balance the rigor of mathematical formalism with the psychological difficulty of imagining a universe that does not follow the rules of lived experience. Moreover, the philosophical consequences extend into cosmology. The study of singularities, both in black holes and at the Big Bang, emphasizes that time may have different characteristics depending on location and scale. Near a singularity, space-time curvature approaches infinity, and general relativity no longer provides a complete description. Quantum effects become significant, suggesting that time could fluctuate or lose meaning entirely at the smallest scales. For those analyzing data from gravitational waves or high-energy particle collisions, this introduces an unsettling consideration. Time itself may not be a universal parameter, but an emergent property, arising from statistical averages of complex systems. The cultural and emotional resonance of this work cannot be ignored. Historically, humans have sought to reverse time through ritual, art, and myth. The scientific pursuit of understanding time's flexibility is, in a sense, an extension of that impulse, an effort to comprehend and, if possible, manipulate what has long been perceived as immutable. Yet the discoveries also highlight the limits of human control. Time, while theoretically reversible under certain physical conditions, remains overwhelmingly directed in one orientation for any system of practical scale. Even in quantum experiments, where temporary decreases in entropy have been observed, reversals exist only fleetingly and at microscopic scales. Ethically and philosophically, the implications are profound. If time reversal were possible on macroscopic scales, notions of responsibility, causation, and consequence would be fundamentally altered. Decisions could, in theory, be undone, events unmade. For scientists, even contemplating such scenarios carries weight. The pursuit of knowledge becomes not merely academic, but existential, raising questions about the nature of reality, determinism, and the human role within the universe. In laboratories, observatories, and computational models, physicists continue to confront these tensions. Every new measurement, every refined simulation, emphasizes the disconnect between perception and the fundamental behavior of space-time. The human mind is anchored to a forward-moving sequence of moments, but the universe itself is indifferent to this limitation. Data from black holes, relativistic jets, and quantum systems all confirm that time is flexible, constrained by physical laws, but not by intuition. Ultimately, this conflict between discovery and perception defines the experience of studying time. Scientists must navigate the cognitive dissonance of working with a reality that behaves differently from human expectation. They must reconcile awe with uncertainty, excitement with apprehension. While the arrow of time governs daily life, their work continually reveals that, in principle, time could move in unexpected directions. The human mind resists, but the universe does not yield to resistance. And it is precisely in this dissonance, between what is observed and what is imagined, between the familiar and the extreme, that the pursuit of understanding time finds its deepest resonance. In the early 1970s, experimental science began to catch up with theory, providing tangible evidence that time is not absolute. The Hartle-Keating experiment stands as a landmark in this effort. Atomic clocks were flown on commercial airliners circling the globe, some eastward, others westward, while identical clocks remained grounded. Upon comparison, the results were unmistakable. The airborne clocks had experienced time differently. Seconds had slipped at different rates, depending on speed and altitude. This experiment transformed time from an abstract concept into a measurable, physical quantity, confirming Einstein's predictions and demonstrating that motion and gravity shape the flow of time itself. At the same time, quantum physics revealed phenomena that challenged classical intuition even further. Certain interactions at the subatomic scale display reversibility, meaning that processes can, in principle, run both forward and backward without violating fundamental laws. Experiments involving photon entanglement and controlled quantum systems have shown that the behavior of particles is not inherently tied to a single temporal direction. While these reversals are microscopic and fleeting, they confirm a critical point. The laws of physics themselves are largely indifferent to the direction of time. Further hints emerged from particle physics at CERN. Experiments with antimatter revealed small asymmetries in the behavior of particles versus a phenomenon known as CP violation. These deviations are subtle but significant. They suggest that, while most interactions are time-symmetric, the universe does contain mechanisms that favor one temporal direction over another. Such findings deepen the mystery, showing that time is both flexible and constrained, capable of symmetry under some conditions, yet biased by statistical and quantum effects in others. Parallel to these laboratory discoveries, computational simulations began to provide insight into extreme environments where time could behave in ways impossible to reproduce on Earth. Models of matter near black holes indicate that, for external observers, the flow of time appears to slow dramatically or even reverse along closed time-like curves predicted by relativity. Particles spiraling toward the event horizon seem to freeze, looping in ways that suggest the potential for temporal inversion, at least in the perspective of an observer distant from the gravitational source. These simulations highlight that extreme mass and curvature can create conditions where the usual assumptions of temporal progression break down. In recent years, experiments with time crystals have added another layer of understanding. These novel states of matter do not repeat in space, as ordinary crystals do, but in time. Their internal motion recurs periodically, creating a stable, oscillating system that violates traditional temporal symmetry. While they do not reverse time in the conventional sense, they demonstrate that the rules governing temporal behavior are not immutable. Laboratory systems can be engineered to exhibit cycles and patterns that challenge classical expectations. revealing that time itself can be structured in unusual and controlled ways. Taken together, these investigations show a consistent pattern. The apparent directionality of time is not a universal requirement. Motion, gravity, quantum interactions, and extreme environments all influence the flow of seconds and moments. What seems fixed in daily experience is flexible under controlled or extreme conditions. The laboratory confirms what mathematics and theory have long suggested. Time is a physical property, responsive to forces and context, not an unchangeable background, and if these principles hold in carefully controlled experiments on Earth, then it raises a larger question. In the vast high-energy, high-gravity environments scattered throughout the cosmos, could these effects amplify? If time can be bent, delayed, and even oscillated in the laboratory, perhaps among the stars, under the immense gravitational pull of black holes, or in the heart of collapsing matter, time's flow could behave in ways entirely foreign to human intuition. The early investigations have illuminated the path from atomic clocks to quantum states, from particle accelerators to computational models. Each discovery edges closer to the possibility that time's arrow is not only bendable, but may, in extreme circumstances, be reversed. The implications of these experiments extended beyond verification of relativity and quantum mechanics. They provided the first practical insights into the malleability of time itself. In the Haffel-Keating experiment, the magnitude of the observed time dilation was small, mere nanoseconds, yet the significance was profound. The results confirmed that even ordinary motion and gravitational differences could measurably alter the passage of time. GPS technology would later rely on these findings to correct satellite clocks, illustrating that time discrepancies, once theoretical, have practical consequences in systems operating at high velocity or altitude. It became clear that time is not a universal constant, but a local property influenced by the environment. In quantum systems, the reversibility of particle interactions provided a glimpse into the deeper nature of temporal mechanics. Experiments with entangled photons demonstrated that under highly controlled conditions, the evolution of a system could proceed identically forward and backward. These observations revealed that time's apparent direction is statistical rather than absolute. For a single particle or a small system, the probabilities governing state transitions do not inherently favor one direction of time. Only when systems become large and entangled with their environment does entropy impose the familiar arrow of time, giving rise to the irreversible processes observed in everyday experience. At CERN, studies of CP violation in mesons and other subatomic particles offered a more nuanced understanding of time symmetry. While most interactions are time symmetric, these subtle asymmetries indicate that the universe has a built-in preference, however slight, for a forward progression of events. The discovery is crucial. It explains, in part, the dominance of matter over antimatter in the universe, allowing stars, planets, and life to exist. It also demonstrates that while time can be reversible under controlled conditions, natural systems are subject to biases that enforce an overall temporal direction. Computational models of black holes and relativistic systems provided further evidence that time can appear to behave differently depending on perspective. Particles approaching an event horizon experience extreme gravitational time dilation, appearing to an external observer to slow, pause, and even loop along predicted trajectories. Simulations indicate that in rotating black holes or Kerr geometries, closed time-like curves are mathematically possible. Although they are highly sensitive to perturbations, these results confirm that the potential for temporal reversal exists in theory, even if macroscopic realization remains improbable. Time crystals introduced a novel laboratory analog of temporal manipulation. Unlike conventional crystals, which repeat their atomic structure in space, time crystals exhibit motion that repeats periodically in time, creating a form of temporal order. This discovery demonstrates that physical systems can be engineered to break conventional time translation symmetry, offering a tangible example of non-standard temporal behavior. While these effects do not constitute macroscopic time reversal, they provide proof of principle under specific conditions. Time can be structured in ways fundamentally different from everyday experience. Collectively, these early investigations establish a pattern. Time is neither absolute nor immutable. It is influenced by motion, gravity, quantum mechanics, and engineered conditions. Observations at microscopic and astronomical scales demonstrate that the flow of time is context-dependent, subject to modification under extreme conditions, and, in principle, capable of reversal. The laboratory, the particle accelerator, and the computational model all point to the same conclusion. Temporal behavior is a property of physical systems, not a universal law. These findings also highlight the interplay between observation and interpretation. Even when time behaves unusually, human perception remains anchored to forward progression. We can measure differences in clock rates, observe particle reversals, and simulate loops near black holes, yet our conscious experience is limited to a single temporal direction. The early investigations reveal the boundary between measurable phenomena and perceptual intuition. They show that while physics permits flexibility, the macroscopic universe largely adheres to a forward arrow due to statistical and entropic constraints. If time can be manipulated in laboratories and modeled accurately in simulations, the next question becomes inevitable. What might occur in environments beyond Earth, where energy densities, gravitational forces, and quantum effects are far more extreme? Early investigations have laid the foundation for this inquiry. They have demonstrated that time is responsive, conditional, and, under certain circumstances, capable of behaviors far removed from ordinary experience. Among the stars, in the intense gravitational fields of black holes or the quantum foam of the early universe, the theoretical possibility of temporal inversion moves from abstract mathematics toward physical plausibility. The laboratory experiments, high-energy observations, and computational models collectively illuminate a universe in which the rules of time are not fixed, but flexible, waiting for the conditions in which the arrow may bend or even reverse. At the boundary of a black hole, known as the event horizon, time begins to behave in ways that are both measurable and profoundly unsettling. According to general relativity, the immense gravitational pull near the horizon slows time relative to distant observers. A spacecraft descending toward the event horizon would appear to freeze in motion from afar, its signals increasingly redshifted until they vanish entirely. For the observer inside, however, the descent continues normally, seconds ticking with familiar regularity. The disparity between perspectives highlights a fundamental truth. Time is not universal. It is a property contingent on position, velocity, and gravitational influence. Beyond the horizon, theoretical models suggest even stranger possibilities. At the singularity, the core of a black hole where density approaches infinity, space-time itself breaks down. Mathematicians have speculated that under such conditions, the familiar roles of space and time may interchange. What we perceive as temporal progression could become a spatial dimension, while what we consider space may take on the qualities of time. In such a regime, the direction of time as humans experience it may lose meaning, and conventional notions of cause and effect may no longer apply. These are not mere abstractions. They emerge directly from the equations of general relativity, though they remain beyond current observational reach. White holes, the theoretical counterparts of black holes, present an equally intriguing scenario. Unlike black holes, which absorb all matter and energy that crosses their horizon, white holes expel everything, forbidding entry. In the context of time, they suggest a reversal of processes, a localized unmaking rather than making, a region where events unfold opposite to ordinary temporal progression, while no white hole has been observed. Their mathematical consistency demonstrates that general relativity does not exclude the possibility of regions where time's arrow is fundamentally different. Einstein-Rosen bridges, or wormholes, extend this speculation further. These structures connect distant points in space and, theoretically, in time. A traversable wormhole could link to separate moments, allowing a path through which time might effectively be reversed for travelers moving within it. While the practical construction or stabilization of such a bridge remains far beyond current technology, the equations indicate that the fabric of the universe permits connections between past and future under extreme conditions. The implications for causality and temporal order are profound. The universe may contain pathways where events are not constrained to the familiar sequence of before and after the early moments of cosmic inflation, provide another perspective on the extremes of temporal behavior. During the first fractions of a second after the Big Bang, the universe expanded exponentially, and the flow of time may have been radically different from what we experience today. Some cosmologists propose that the direction of the arrow of time was established only after inflation stabilized the universe's large-scale structure. Before that, temporal order may have been undefined or even fluctuating, suggesting that the universe itself had to choose a direction in which events would progress. At these edges, where black holes, wormholes, and the quantum nature of space-time converge, the familiar rules of physics blur. Cause and effect, past and future, begin to dissolve into mathematical possibilities. Time is no longer a steady river flowing uniformly. It is a variable, a dimension contingent on mass, motion, and energy. The extreme edge of science shows that temporal behavior is not monolithic. It can slow, bend, oscillate, and, under the right conditions, reverse. For scientists, this boundary is both a challenge and an invitation. Observing, simulating, and theorizing about such regions stretches the limits of instrumentation, computation, and imagination. Every step closer to these extremes provides new insight into the fundamental structure of reality and forces, a reconsideration of deeply held assumptions at the event horizon and in the hypothetical interiors beyond. The universe presents a vision in which time is not an immutable backdrop but a dynamic, malleable feature, one whose full behavior remains to be understood. And as exploration continues, one question persists. If the cosmos contains regions where time's flow can be halted, twisted, or reversed, how close are we to witnessing them? And what would it mean for our understanding of causality, existence, and the very nature of reality itself? At the edge of a black hole, physics blurs, and with it, the meaning of past and future begins to dissolve. Beyond the event horizon, theoretical physics continues to probe scenarios that push the limits of understanding. In the interiors of black holes, equations derived from general relativity indicate that tidal forces become extreme, stretching matter and radiation along the radial direction in a process called spaghetti. While this is a mechanical description, the implications for time are equally profound. Any observer crossing the horizon would experience proper time normally, yet from an external vantage point, their journey would appear frozen. This duality reinforces that temporal experience is relative. It depends on the frame of reference and the intensity of gravitational fields. Mathematical models of rotating or Kerr black holes introduce further complexity. Their spin distorts spacetime into a twisted geometry, creating frame-dragging effects that could, in principle, form closed time-like curves. These curves are solutions in which a path through spacetime could return to its own past. While the stability of such structures is questionable, small perturbations could destroy them. Their existence in theory demonstrates that the fabric of the universe accommodates pathways where chronological order is not strictly enforced. The implications are significant. Under extreme gravitational and rotational conditions, the unidirectional flow of time may break down locally, even if entropy continues to increase globally. White holes, though hypothetical, offer an intriguing counterpoint. If black holes absorb matter irreversibly, white holes represent the mathematical inversion, ejecting matter and radiation while preventing any ingress. From the standpoint of temporal mechanics, a white hole functions as a region where causal sequences appear reversed compared to ordinary experience. In simulations that combine black and white hole geometries, matter falling into a black hole and emerging from a white hole would trace a path that, externally, seems to reverse events. While such structures have not been observed, they remain solutions to Einstein's field equations, illustrating that general relativity does not forbid local inversion of time. Wormholes extend this conceptual framework further, connecting to distant points in space. They theoretically provide shortcuts through spacetime, potentially linking different temporal moments. Traversable wormholes require exotic matter to stabilize against collapse, but their mathematical formulation demonstrates that the universe could, under precise conditions, host pathways where movement through time is conceivable. These structures challenge fundamental assumptions about causality. They suggest that chronological sequence is not absolute, and that physical laws may permit shortcuts or loops through temporal dimensions under extreme constraints. Quantum mechanics adds another layer to the edge of science. At Planck-scale energies, spacetime may not be continuous but discrete, composed of fluctuating quantum units. In these regimes, time may lose its classical meaning entirely. Theoretical models suggest that temporal order could fluctuate randomly, with micro-reversals occurring at subatomic scales. Combined with relativistic effects, this indicates that the early universe and extreme gravitational environments may host conditions in which time behaves non-linearly, temporarily reverses direction for localized regions. Cosmic inflation also suggests that time's arrow is not fixed universally. During the exponential expansion of the early universe, thermal and quantum fluctuations would have dominated, and the establishment of a consistent temporal direction likely emerged only after large-scale stabilization. In this context, the orientation of time as we perceive it today is a product of initial conditions and symmetry-breaking processes, implying that other regions of spacetime could, in principle, exhibit different temporal behavior at the extreme edge of science, where black holes, white holes, and quantum fluctuations intersect. Conventional notions of past, present, and future dissolve. Time is neither uniform nor absolute. It can slow, stretch, oscillate, and, under extreme conditions, locally reverse. These frontiers demonstrate that the universe is more flexible than intuition suggests, and that the laws governing time are contingent upon environment and scale. The pursuit of understanding these phenomena continues to push observational astronomy, high-energy physics, and computational modeling to their limits. Every simulation of a spinning singularity, every exploration of a theoretical wormhole, and every calculation of Planck-scale dynamics extends the frontier of what is knowable. The extreme edge of science reveals a universe in which time is not a fixed river, but a dynamic, mutable dimension, a feature of reality that challenges the assumptions embedded in human perception and opens the possibility, however remote, of temporal inversion under the right cosmic conditions in mainstream physics. The concept of time is closely tied to observable asymmetries, most notably the thermodynamic arrow. Entropy, the measure of disorder in a system, provides a fundamental explanation for why events unfold in a single direction. In any closed system, microscopic interactions occur according to time-symmetric laws, but when considered collectively, they produce macroscopic irreversibility. A cup of coffee cools, ice melts, and stars burn their fuel, processes that move from low to high entropy. The forward progression of these changes defines our experience of past and future, anchoring daily life to a unidirectional flow. Complementing the thermodynamic arrow is the cosmological arrow of time, which emerges from the universe's large-scale dynamics. Since the Big Bang, the universe has been expanding, creating an overall temporal orientation. Galaxies drift apart, cosmic voids widen, and the large-scale structure evolves toward increasing separation and dilution. This expansion is not merely spatial. It imposes a directional framework on the evolution of all systems within it. In essence, the stretching of space itself aligns with the progression of time, providing a universal context for the otherwise localized increase in entropy. The radiative arrow offers yet another manifestation of temporal asymmetry. Light, as electromagnetic radiation, consistently travels outward from sources, dispersing energy into surrounding space. Photons emitted by stars, supernova, or cosmic processes move away from their origin, never spontaneously converging to recreate their source state. This directional bias reinforces the perception of time's forward march, linking the movement of energy to the unfolding of events. Observational astronomy relies on this principle, using the propagation of light to reconstruct cosmic history, effectively reading a record that moves from past to present. At the quantum scale, decoherence provides a microscopic explanation for the emergence of irreversibility. Wave functions, which describe the probabilistic states of particles, evolve according to time-symmetric equations. However, when a system interacts with its environment, superpositions collapse into definite outcomes. This process of decoherence effectively enforces a direction on quantum events, producing the classical reality in which time appears irreversible, while the underlying equations do not prefer a temporal direction. The interaction with large environments creates the emergent arrow of time that dominates macroscopic observation. Evidence from the cosmic microwave background further illustrates time's forward orientation. The radiation left over from the Big Bang serves as a fossil record of the universe's early state, encoding information about density fluctuations and thermal conditions billions of years ago. These imprints reveal a universe evolving from an initially highly ordered configuration toward progressively higher entropy. They provide a concrete, observable manifestation of the thermodynamic and cosmological arrows combined, showing that time's direction is not a human construct, but a measurable aspect of physical reality. Together, these mainstream models form the foundation for understanding temporal progression. Each arrow, thermodynamic, cosmological, radiative, and quantum, offers a consistent explanation for why time appears to move forward, why events unfold sequentially, and why causality is preserved in observable systems. They define the rules by which everyday phenomena, stellar evolution, and cosmic history operate. The universality of these arrows underpins both theoretical frameworks and practical technologies, from particle physics to satellite navigation, and establishes a coherent picture of time as a directed dimension. Yet, despite their explanatory power, these frameworks leave open fundamental questions. Why did the universe begin in a state of exceptionally low entropy, creating the conditions for the thermodynamic arrow? Could regions of space-time exist where these arrows do not align, or even point in the opposite direction? While mainstream science describes the overwhelmingly consistent forward motion of time, some theoretical models suggest that, under extreme or exotic conditions, the universe might host exceptions, places where the familiar sequence of past, present, and future could be disrupted, or perhaps even inverted. These considerations form the threshold between established physics and speculative frontiers. The mainstream arrows explain the overwhelming directional consistency observed across the cosmos. Yet they also frame the puzzle. If time is fundamentally a physical property tied to entropy, radiation, expansion, and decay, could there exist environments where these guiding principles break down, permitting alternative temporal behavior? The universe, it seems, may hold hidden possibilities, a second arrow pointing the other way, waiting to be revealed under conditions far beyond ordinary experience. The thermodynamic arrow, while foundational, raises deeper questions when considered on cosmological scales. Entropy increases locally in almost every observed system. But why did the universe begin in such a remarkably low entropy state? Current models suggest that the initial conditions of the Big Bang were highly ordered, creating a vast potential for entropy to increase over billions of years. Without this extreme initial order, the directional flow of time we observe would not exist. This low entropy beginning is not explained by the thermodynamic arrow itself. It is a boundary condition imposed on the universe, a starting point that defines the asymmetry we now perceive as forward-moving time. Cosmologists have investigated whether regions of the universe could exist where entropy behaves differently. Some inflationary models propose that while our observable universe follows a clear thermodynamic gradient, other domains beyond our observational horizon might evolve under different conditions. In such regions, entropy could decrease locally, producing processes that appear to reverse the conventional arrow of time. These possibilities remain speculative, as no empirical evidence yet supports their existence. But the mathematical consistency of such models indicates that the laws of physics do not strictly forbid them. Radiative processes also illustrate the universality of temporal asymmetry. The outward propagation of light is intimately linked to energy dispersal and thermodynamic gradient. Photons emitted from stars carry energy away, increasing the overall disorder of the surrounding medium. Observing these processes allows astronomers to reconstruct past events, supernova explosions, galaxy formation, and cosmic structure evolution, demonstrating that radiation itself encodes a directional record of time. Yet, theoretically, in regions of space where conditions are highly unusual, extreme gravitational fields, or engineered energy configurations, light might behave differently relative to local observers, creating scenarios in which radiative asymmetry could be locally modified. Quantum decoherence adds another layer of temporal complexity. While isolated quantum systems evolve according to time-symmetric equations, interaction with an environment produces effective irreversibility. The emergent arrow of time in these systems depends on entanglement and information dispersal, tying microscopic events to macroscopic time's flow. Experiments in controlled environments, such as ultra-cold atoms or trapped ions, have demonstrated temporary reductions in entropy or partial reversals of quantum evolution. Although these effects are transient and occur at microscopic scales, they suggest that time's arrow is not an absolute property of nature but an emergent feature of system size and environmental interaction. The cosmic microwave background (CMB) further illustrates the alignment of multiple temporal arrows. Its uniformity and slight anisotropies encode the expansion and thermodynamic state of the early universe. Observations from satellites like COBE, WMAP, and Planck have measured these fluctuations with high precision, providing a snapshot of the universe approximately 380,000 years after the Big Bang. The CMB acts as a temporal reference, a directional marker confirming the forward progression from a high order, low entropy beginning toward increasingly disordered and structured configurations. Together, these mainstream frameworks demonstrate a consistent, coherent picture of time's direction. The thermodynamic arrow provides local justification. The cosmological arrow situates it within universal expansion. The radiative arrow reinforces energy dispersal, and quantum decoherence explains microscopic emergence of irreversibility. Each arrow supports the others, forming a network of principles that ensures time progresses in a single direction for observable systems. Yet the question persists: are these arrows absolute across all possible conditions, or do extreme or exotic environments permit deviations? While mainstream physics describes a highly consistent, forward-moving time across known systems, the theoretical possibility remains that, under conditions of extreme gravity, high energy density, or unusual quantum states, time might behave differently. This gap between empirical observation and theoretical allowance defines the boundary where established science ends and speculation begins, hinting at the existence of mechanisms or regions in the universe where a second, reversed arrow of time could exist, waiting to be discovered. The mainstream arrows of time explain what we observe and measure, but they do not close the question. They reveal consistency, direction, and predictability, yet simultaneously frame a larger mystery. The universe may contain regions or conditions where the familiar flow of time breaks down or even inverts. Understanding these boundaries requires moving beyond conventional models and exploring extreme physics, from black holes to early universe cosmology, setting the stage for theories that challenge the very notion of unidirectional time. Speculative models push the boundaries of physics, exploring conditions under which time may not only bend or slow, but potentially reverse. One such idea arises from CPT symmetry, a fundamental principle in quantum field theory stating that if charge parity and time are simultaneously inverted, the underlying laws remain unchanged. Extending this principle cosmologically, some theorists propose a mirror universe, a twin cosmos expanding in the opposite temporal direction from our own. In this scenario, the Big Bang is a central point of symmetry, while our universe evolves forward. Its mirror counterpart evolves backward. From an external perspective, events in that universe would appear to move in reverse, creating a coherent but counterintuitive temporal reflection. Loop quantum cosmology offers a related, though distinct, speculative framework. By applying principles of quantum mechanics to the fabric of spacetime itself. These models suggest that classical singularities, like the Big Bang, are replaced with a big bounce at the Planck scale, where quantum gravitational effects dominate. Time may reverse locally, causing contraction to expand again. This model eliminates the singularity's infinite density, replacing it with a cyclic process in which temporal direction is contingent upon the universe's phase. If correct, time's flow is not fixed but can flip under extreme cosmic conditions, implying that what we experience as a linear arrow is only one segment of a potentially oscillating continuum. Retrocausality in quantum physics challenges our most basic intuitions. Certain interpretations of quantum mechanics, particularly in entanglement experiments, suggest that measurements can influence prior states of a system. While still debated, these effects indicate that at the quantum level, cause and effect may not adhere strictly to forward progression. Photons in delayed choice experiments, for example, appear to decide their history after an observation occurs, hinting at a universe in which temporal order is more fluid than classical perception allows. Though these phenomena do not manifest in macroscopic systems, they demonstrate that time may operate differently at fundamental scales. Multiverse theories provide yet another speculative avenue. In frameworks positing multiple or parallel universes, it is mathematically plausible that some domains experience temporal flow opposite to our own. These universes would evolve from initial conditions similar to ours, but with reversed entropic gradients, radiation directionality, or quantum interactions. In principle, they could host processes that appear as time reversal relative to our frame of reference, while observational confirmation remains beyond reach. The conceptual consistency of such models reinforces the possibility that time's arrow is not universal but contingent, a property emergent within specific regions of a broader multiversal landscape. Hawking's chronology protection conjecture addresses the limits of these possibilities. Proposed to prevent causal paradoxes, such as the grandfather paradox. It suggests that the laws of physics may inherently resist macroscopic time, loops, or traversable pathways that would allow direct reversal of events. While this conjecture does not entirely forbid regions where time behaves unusually, it implies constraints on the practical realization of time reversal, ensuring that the universe maintains overall consistency and avoids contradictions. Essentially, time may bend, oscillate, or locally invert, but global causality remains protected. Together, these speculative and fringe theories present a vision of time as a property both robust and malleable. In certain extreme or carefully constrained scenarios, the arrow of time might reverse or diverge, either in mirror universes, within quantum scale bounces, or in exotic space-time geometries. These models do not necessarily violate known physical laws. Instead, they suggest that time's forward progression is contingent on local conditions, boundary states, and symmetries embedded in the cosmos. If such reversals exist, They may be part of a larger equilibrium, a hidden symmetry ensuring that while our universe experiences a forward arrow, other domains or scales preserve a form of temporal balance. In this speculative framework, time reversal is not chaos but complementarity, a countercurrent woven into the universe's structure, hinting at an order that is invisible from the perspective of everyday experience. The universe may thus contain regions where past and future exchange roles, not arbitrarily, but according to deep underlying principles, maintaining harmony across space, scale, and time. Expanding on these speculative ideas, loop quantum cosmology offers insight into how time reversal might operate in extreme regimes. By quantizing spacetime, this framework eliminates singularities like those at the Big Bang or inside black holes, replacing them with discrete units of temporal and spatial evolution. When spacetime contracts toward a high-density state, the reversal of temporal direction becomes mathematically possible as the universe transitions from contraction to expansion. In this scenario, the flow of time is not linear or absolute, but dependent on cosmic phase transitions, creating a model in which the universe could undergo cycles of forward and reversed temporal flow, each bounded by quantum gravitational constraints. Mirror universe models, derived from CPT symmetry, further explore the possibility that temporal direction is relative. If our universe has a mirrored twin expanding backward in time, events in that twin would unfold as reversals from our perspective. Matter formation, entropy gradients, and even radiative processes would operate in opposition to our arrow of time. While no direct observation can currently confirm such a universe, the model aligns with the laws of physics, demonstrating that the universe allows solutions in which time is symmetric on a global scale, even if locally it appears unique. This suggests that the asymmetry we perceive is emergent rather than fundamental, a consequence of initial conditions in our particular cosmic domain. Multiverse frameworks add another layer of plausibility to temporal reversals. In cosmologies with multiple expanding domains, some universes may follow opposite entropic gradients, with energy dispersal, particle interactions, and radiation behaving as if time is running backward, while our observations are limited to a single cosmological horizon. The mathematics of inflationary cosmology and string theory accommodates regions where physical laws operate with inverted temporal orientation. This highlights a key distinction. The forward arrow of time in our observable universe may not be a universal principle, but a local phenomenon contingent on the specific configuration of matter, energy, and initial conditions. Hawking's chronology protection conjecture sets boundaries on these possibilities, while equations allow for time loops, closed time-like curves, and local inversions. Physical mechanisms such as energy conditions, quantum instabilities, or feedback from vacuum fluctuations appear to prevent paradoxical macroscopic violations of causality. Essentially, even if regions exist where time reverses or loops, they are constrained in ways that preserve the overall logical structure of events across the universe. Any time-reverse domain would thus operate under local rules, insulated from creating contradictions in the broader spacetime fabric. Taken together, these speculative models illustrate that time may not be universally linear. Across quantum systems, mirror universes, cyclic cosmologies, and extreme gravitational environments, the flow of time can bend, oscillate, or even reverse, consistent with physical laws. These phenomena, while beyond current observational reach, are not dismissed as impossible. Instead, They reveal the potential flexibility embedded within space-time itself. Time's arrow, in this context, is a local emergent property, one direction among many permitted by fundamental symmetries, boundary conditions, and quantum rules, if such reversals exist. They hint at a deeper cosmic balance. The universe may host domains where temporal flow is inverted, yet overall equilibrium is preserved through symmetry and conservation. Far from a paradox, time reversal becomes part of the hidden architecture of reality, a subtle photonic current flowing alongside the familiar forward progression, suggesting that our understanding of past and future is limited to our local slice of a far more complex temporal landscape. Modern science has advanced to the point where previously theoretical constructs can now be observed, measured, and tested, bringing humanity closer to understanding time not just as a concept, but as a tangible aspect of the universe. The Event Horizon Telescope, a global network of radio observatories, has produced the first direct images of black holes, capturing the distorted light from matter spiraling at near light speeds around the event horizon. These observations provide unprecedented insight into the curvature of space-time under extreme gravity. By examining how light bends in orbits, researchers can infer how time behaves near singularities, confirming that clocks near these regions would experience significant dilation, and hinting at conditions where temporal order may appear disrupted to outside observers. Gravitational wave observatories, such as LIGO and Virgo, have opened an entirely new window onto the dynamics of spacetime itself. Collisions of massive black holes and neutron stars generate ripples that propagate through the cosmic fabric at the speed of light, carrying information about the extreme curvature of spacetime. These waves confirm that spacetime is flexible, capable of oscillation and deformation, and that time is inherently linked to the geometry of the universe. Each detection allows physicists to test general relativity under conditions far beyond terrestrial laboratories, refining models of time dilation and offering glimpses into environments where conventional temporal progression could be altered. Quantum experiments are now testing the very foundations of temporal order. Researchers have successfully created superpositions of events where the sequence of operations is not fixed, a phenomenon known as indefinite causal order. Photons and entangled particles in these experiments demonstrate that, at the microscopic level, the conventional before and after may lose its meaning. While these effects are confined to small scales, they offer a proof of principle. Time's direction is not absolute, and quantum systems can exhibit behavior consistent with temporary or local reversal of temporal order. Simulated universes and computational modeling are extending these investigations into regimes impossible to probe directly. Using AI-driven simulations, physicists model scenarios involving extreme gravity, high-density quantum states, or exotic matter, predicting the conditions under which time could slow, loop, or reverse. These simulations test hypotheses from both mainstream and speculative frameworks, exploring the dynamics of closed time-like curves, bouncing cosmologies, and hypothetical regions where entropy decreases. The results provide a virtual laboratory to examine the behavior of time under conditions beyond current. Experimental reach, the study of dark energy and the universe's accelerated expansion, also intersects with temporal research. Cosmic acceleration influences the thermodynamic and cosmological arrows of time, and some theorists have suggested that under certain conditions, expansion could alter entropy trends on vast scales. While highly speculative, this raises the possibility that distant regions of the universe, or even the universe as a whole in the far future, may encounter phases where conventional forward time evolution is disrupted or inverted. Each of these efforts represents a frontier where observation, computation, and theory converge. Black holes, gravitational waves, quantum experiments, and cosmological modeling all provide incremental understanding of how time functions, how it can be manipulated, and how it may behave under extreme or exotic conditions. While humanity remains far from creating or encountering macroscopic time reversal, these investigations map the boundaries of possibility, testing both classical and unconventional theories. As scientists probe deeper, they confront the paradox that time is simultaneously a measurable property, a dimension shaped by matter and energy, and a malleable construct in extreme regimes. Every detection, simulation, or quantum experiment acts as a mirror, reflecting both what is known and the vast unknown. The closer researchers get to decoding time, the more it seems that our understanding is embedded within its own reflection, a dimension that can be bent, stretched, and possibly inverted, yet remains an essential framework for the universe itself, beyond observational and experimental efforts. Theoretical physics continues to guide modern research into time's nature. In particular, collaborations between quantum information theorists and cosmologists are exploring how the fundamental structure of spacetime could allow deviations from conventional temporal flow. Ideas such as holographic duality suggest that the three-dimensional universe we experience may be encoded on a two-dimensional boundary, implying that time itself could emerge from deeper, non-classical degrees of freedom. If temporal order is emergent rather than fundamental, then, under extreme conditions near black holes at the quantum gravity scale, or in early universe phases, time may behave differently than our macroscopic intuition predicts. In contemplating the reversibility of time, humanity confronts not only a physical mystery but an existential one. Our perception of reality is deeply bound to memory. The mind organizes experience into a coherent narrative of past, present, and future. Neuroscience shows that this temporal framework is constructed, an internal chronology created to interpret the external world. Yet, if time is not absolute, its flow can bend, halt, or even reversed, then the very foundation of consciousness comes into question. The now that we cling to, the succession of moments that defines life, may be an emergent feature of entropy rather than an inherent property of the universe. What we perceive as forward progression is perhaps only the lens through which our minds observe the underlying dynamics of spacetime. Philosophically, this challenges the concepts of causality, consequence, and mortality. If time can reverse or loop under certain conditions, the finality of events, including death, becomes less rigid. In extreme regions of the universe, in black holes, across quantum boundaries, or in hypothetical mirror universes, the strict linearity of past and future may dissolve. Such scenarios force reflection on the human experience. If entropy dictates our sense of temporal order, then the universe itself may host realms where life, decay, and existence do not adhere to the irreversible patterns we assume. The notion of an eternal universe emerges naturally from these contemplations. Cyclic models, loop cosmologies, and speculative theories of mirrored temporal domains all imply that the universe has neither a true beginning nor a final end. Time becomes a rhythm rather than a line, a series of expansions and contractions, forward motions and potential reversals. Humanity's limited perception traps us within one segment of this vast temporal continuum. Yet science suggests that the underlying reality may be a seamless oscillation of space-time, indifferent to the direction we observe. This reflection extends to the human search for meaning. If time is flexible, if the arrow we rely on is contingent on entropy and perspective, then the questions that have long driven philosophy, religion, and science converge. Are we observers of an unfolding narrative, or participants in a deeper, cyclical cosmic dance? Does knowledge of time's malleability diminish the significance of choices? Or does it magnify the wonder that any conscious being can exist within such a framework at all? As the journey concludes, the universe itself can be imagined breathing, expansion and contraction, forward and backward motion, each cycle indistinguishable from eternity. Stars ignite and die, black holes twist light and time, quantum systems oscillate, and the cosmos continues in motions that exceed comprehension. The question may never be whether time can reverse in a literal sense, but whether the human mind can ever perceive it in its full scope. In this sense, time is both a mystery and a mirror reflection of the universe and of our place within it. Ultimately, the contemplation of reverse time leaves a lingering sense of humility. The cosmos operates on scales and principles that elude immediate understanding, yet each discovery, each experiment, and each theoretical advance draws humanity closer to the contours of this profound reality. The arrow of time, in its rigidity and potential flexibility, frames not only the cosmos but the human experience, challenging perception, reshaping philosophy, and inviting an awe that is as boundless as the universe itself. The universe continues, its eternal rhythm, indifferent yet observable, a testament to motion, transformation, and the subtle symmetries that may underlie all of existence. And within that vast, silent movement, humanity remains both witness and participant, suspended in a moment that may be linear, cyclical, or entirely relative, forever contemplating the possibility that time itself is not a river, but a landscape, infinite and reversible, waiting to be understood. In the end, the exploration of time's reversibility highlights the unique position of humanity as both observer and interpreter. Our consciousness relies on linear sequences, yet the universe may operate under broader, more flexible principles. Understanding these principles expands scientific knowledge and invites a reconsideration of human perception, memory, and existence itself. Time, in this sense, is both a measurable parameter and a conceptual frontier, a framework in which the universe evolves and a mirror in which humans glimpse the limits of comprehension, challenging us to reconcile experience with the deeper, often counterintuitive truths of reality. Search for time's essence continued not only through instruments and equations, but through quiet introspection. Across observatories, laboratories, and universities, the discussion began to shift from what time is to what it means. Physicists debated not only the mathematics of its reversal, but the implications for identity, causality, and the very notion of existence. If every event could, in principle, unfold backward, then the structure of meaning itself, cause and effect, beginning and end, would lose its foundation. Time would no longer be a one-way river, but a standing field where every event eternally exists, merely perceived differently depending on the preserver's position within space-time. Neuroscience offered an unexpected bridge between cosmology and consciousness. Studies of brain activity revealed that perception of time is not continuous but reconstructed from fragments. assembled milliseconds after events occur. The mind, in essence, is always living slightly behind reality. This realization resonated with the idea of relativity, where simultaneity is relative and the present becomes a localized illusion. If perception already lags behind the universe's true state, then perhaps the feeling of a forward-moving timeline is a cognitive artifact rather than a physical truth. Philosophers re-examined ancient concepts through the lens of modern physics, the cyclical cosmologies of Eastern traditions, the eternal recurrence of the Stoics, and even early theological views of timeless divinity, all found new interpretations within quantum and relativistic frameworks. In some sense, the scientific exploration of time's reversibility brought humanity back to questions that had existed long before the first telescope questions about permanence, transformation, and what it means to exist within a changing universe. From a cosmological standpoint, theoretical models continued to probe whether the universe itself might be symmetric in time. The idea of a mirror cosmos expanding in the opposite temporal direction remained one of the most compelling possibilities. In this scenario, entropy would increase in both directions, away from the Big Bang, creating two universes, one moving forward, the other backward, each perceiving its own flow as normal. Neither would be aware of its twin's reversed arrow of time, yet both would be part of a single, balanced whole. This perspective suggested that time's asymmetry might be a local illusion within a fundamentally symmetric reality. Philosophers of physics proposed that consciousness could act as the boundary condition for time's direction. The collapse of the wave function, which brings quantum possibilities into a single observed reality, might be what defines the sequence of before and after. If observation generates order from potentiality, then perhaps consciousness itself is what enforces the arrow of time, an emergent property of complexity that turns the universe's static symmetry into lived experience.